Well, welcome to this the second session of the day. It's the I think the third session on bioenergy, and I think we'll have a very interesting one today. We have a visitor. We have a guest speaker from Maragra's sugar company in Mozambique. Will be telling us a bit more about the CHP system that they are operating there. That will be after the first break. So we'll start the session with a part on biomass combustion and something about boilers. And then we have the presentation of the case studies and some questions and answers. And following that, we'll be looking a bit more on steam cycles, steam systems, turbines, some calculations, some technical models on this. So let's start. For the conversion of solid biomass to electricity, we basically have two options, and that's either gasification or combustion. And for combustion, we're usually talking about steam cycle systems. So, a boiler producing heat, which is transferred to water, which is evaporated, overheated to produce steam, and that is then used for driving a turbine or a steam engine. Gasification, as we've discussed 2 days ago during that session, is about the conversion of solid biomass to combustible gas, which can then be used for driving a gas generator. Alternatively, also for driving for fueling a boiler, producing steam, but it's more common to use it in gas engines. The choice whether to go for gasification or combustion depends on a number of things. First is biomass properties. Combustion is very versatile and can, use pretty much every type of solid biomass depending on the type of furnace. And gasification is a bit more picky where it comes to the type of biomass and the way that it's presented with respect to the morphology, so the particle size and density, to the moisture content, to the ash content. I'll need to some people. What is furthermore important is the scale of projects. As we've seen yesterday, gasification has some very good efficiency advantages over combustion systems, especially in the smaller scale. Let's say up to a few megawatts. There is quite a big difference in the efficiency. And if you start looking at larger systems, then combustion cycle efficiencies start to be quite similar to those that you can find with gasification systems. And there's a point that is technical risk, and that is very much related to gasification, in that for some types of systems it proves to be more difficult to operate and maintain them, which has a lot to do with, well, let's say being able to get the biomass at the right specifications for the gasifier, but also to the level of maintenance on the gasifier itself and the engines. The potential fluctuations in systems, the the loading rate of gasifiers, which might be causing problems. So all this makes combustion let's say a bit more stable and a bit more reliable than gasification. That's not to say that all gasification systems are inherently risky, but let's say I think there's more gasification systems that show problems than there are combustion systems. The figure that we see here, I'll turn on the laser pointer, is a quite typical combustion system where you have a certain biomass supply which is stored for a certain time. You'll often have some preparation and processing before it can be fed to the boiler. This would be the boiler itself, producing steam, driving a turbine, which in turn drives a generator. Steam is condensed, turned back to water, and returned to the boiler. That's basically the steam cycle there. First, looking at storage, this is quite important, basically for any bioenergy project, particularly solid bioenergy projects, because there's always going to be some need to assure a continuous supply of fuel, and in cases where the biomass is produced in a seasonal way, for example, when it's connected to agriculture or agro-processing, maybe needs to store biomass for a longer period, let's say weeks, 2 months. There can be daily fluctuations due to let's say the transportation, for example, of biomass. So it means that you always need to have a certain quantity of biomass in stock, so that if there's no supply for part of the day or for a few days, that the system can continue operating. And it's important to have continuous feeding of a system, and for that there's often systems for bunkering of biomass, meaning that the system is automatically fed from a small storage called a bunker. For storage, it's important to consider the volume that is needed, and that is related on the one hand to the storage time. So obviously, if you need to store biomass for a month, you need to have more storage capacity than when you need to store it for 1 day. And bulk density. So let's say if you have a dense form of biomass with a high bulk density, it means that every cubic meter of fuel that you have contains more kilograms of fuel than when you have a low bulk density. Third point to consider is safety, especially with dry types of biomass. You can have fire hazards due to self-heating. Let's say temperature increases due to bacterial activity, and potential dust explosions. Let's say very fine dust particles of biomass can basically explode if there is a ignition source available. Biomass preparation, usually talking about sizing and drying. Sizing can be reduction of size, for example, by chipping of logs or branches of wood, or by milling, and that's quite often done by a larger scale applications, for example, where biomass is fed into coal-fired power plants. Some systems may also need to have, let's say, larger biomass sizes, and when the available biomass is fine and dusty, it could be agglomerated, forming pellets or briquettes, which can then be fed to the combustion system. Drying is not always needed for combustion systems. Let's say, depending on the design of furnaces, a very wet biomass can actually be combusted, where drying actually takes place in the furnace as a first step of the conversion process. Nevertheless, it can to some extent improve the efficiency, because, let's say, if you have dry biomass that does not cause too much water vapor to be formed inside the furnace, you can achieve higher combustion temperatures, and you may need less energy for evaporation of the water. It's important to always weigh the advantages of drying against the costs, because having a drying system, it requires either investments, or in case of let's say drying on the air, it requires some space to keep the biomass while it's drying. Consumption of energy for drying. If it can be dried outside, then you don't have to do that much, and you don't consume any energy, but it goes slowly, and it very much depends on the humidity, the average humidity level of the air. If you have a very high relative humidity, then drying goes very slowly, or even not at all. If you do consider drying, let's say forced drying by actual heating or ventilation, then it's best to consider the use of waste heat, for example, from coming out of the turbine. So the low temperature heat that could be made available for drying. The combustion process itself is a chemical process, a thermochemical process, where biomass reacts with an excess amount of oxygen in air for production of heat. Now, if we look at what that means, biomass containing primarily carbon, hydrogen, and oxygen. That can be represented by this simple formula. Plus oxygen reacts and forms carbon dioxide, water vapor, and heat. Now, this is a simplified equation, and on this side you will always also have minerals in the biomass, which will end up as ash, and on the other side there'll be water in the biomass, just the moisture content of the biomass itself, which will basically end up along with the water on this side. And with the oxygen from the air that is used for combustion, there will also be a lot of nitrogen coming in. As you know, air contains roughly 20% of oxygen and some 80% of nitrogen. So for every part of oxygen, there will be 4 parts of nitrogen also go into the furnace, and that will come out to some extent as nitrogen on this end, but it will also be to some extent converted to nitrogen oxides on the other side, depending on the combustion temperatures. Say lower temperatures form low quantities of nitrogen oxides, but when temperatures increase, then also the formation of nitrogen oxides will increase. And there will always, to some extent, be some incomplete combustion, depending on how much oxygen is actually admitted into the process. If it's a large excess, then combustion will be more complete than when the amount of oxygen is more or less that what is needed for stoichiometric conversion. And what you can see then is gaseous emissions in the form of carbon monoxide and some polyaromatic hydrocarbons, PAH. Now, what do you see when biomass enters a furnace? Is first the heating of the biomass, because when it's admitted, it will basically be at room temperature. What happens more or less immediately is the water it contains will evaporate. Then the biomass will heat further and will start to pyrolyze, which is more or less the rejection of the volatile compounds in the biomass, and those volatile compounds will start to burn in the next step. And that's that's the burning gases. That's the actual flames that you see when you look at burning biomass. Now, at some point, all the volatiles in the biomass will have burnt out, and what is left is char, and that will continue burning. That's more or less pure carbon, and that will continue to react with oxygen to form CO2. And that will that usually takes a bit longer. Some examples of combustion. We've seen this one in one of the previous slides. That's just cooking, just usually 1 or 2 kilowatts of cooking power. A bit larger system. This is an example for the heating of palm kernels. There you have 10 to 15 kilowatts of heating power for heating these drums with fruits. Similar power, 20, 25, 30 in modern boilers for space heating, used in colder climates. Some boilers in industries. This is a boiler for cashew shell. It's around 3 megawatts or so. This is in palm oil mill in Ghana. I think it's roughly 15 or 20 megawatts. And this is a large steam boiler in a power plant, 30 megawatts or so. What do you see in a boiler? First of all, you'll find more or less optimized conditions for combustion, meaning that the heat is contained within, so that the temperature is high, and the let's say the different stages in the combustion process can be can continue quickly as intended. the fuel supply is controlled. So depending on the actual energy demands, the boiler output can be controlled by controlling the amount of fuel that is added to it. And the air supply is controlled, so that's you don't put in too much air, because it can reduce the combustion temperature, but you don't want to admit too little air, because you get incomplete combustion with emissions and reduced energy output. Secondly, you get an optimized transfer of heat from the burning biomass, from the flue gases that are produced by the burning biomass, to the boiler water. Boiler water flows through pipes, and we'll have a look at that later. And the boiler is constructed such that as much heat as possible is transferred to the boiler water. Most of the heat, I should note, is consumed during the evaporation of the boiler water, because the change from liquids, the phase change from liquids to gaseous state water, steam, consumes a lot of energy, and that is also why water is such a good medium for energy transfer. And a boiler will have systems for the evacuation of flue gases and ash, both from the grates and also from the fly ash from the flue gas. There are different types of boilers. Sorry. We have on the one hand, for the somewhat smaller boilers, although that might not be appropriate to the higher end of the scale range. But we see great furnaces, meaning that the biomass is deposited on a grate. It can be a stationary grate for smaller systems, where biomass automatically rolls down as it burns. We have moving grates, which can be either by moving parts of the grates, which we call a reciprocating grate. So it's the biomass is each step pushed down the grate system. You have let's say horizontal grates called traveling grates, which are more or less chain link grates that on which the biomass is deposited, and which transport the biomass through the furnace as it burns. The combustion air, part of the combustion air, so-called primary combustion air, is blown from under the grate through the grate, so that it reaches the biomass burning on the grate. Secondary air is blown in on a higher point in the furnace. This type of boiler is very flexible. You can basically combust the different types of fuel in one type of boiler, not just biomass, but also coal, for example. You see great boilers, well, especially also in the smaller range of capacity. So from a few hundred kilowatts up to, well, that's indicated here, around 50 megawatt thermal. This is a small video. I hope that it will be running. Yes, this is a reciprocating grate. So you see the different grate parts moving on top of each other. So that once the biomass is deposited on it, these grate parts, as they move in and out, they sort of push slowly the biomass down the grate as it burns. And you see here the airflow of primary air going through the system. And well, here you see let's say the drying biomass. You see the paralyzing biomass, and further down you will see the burnout of the char. And this is an example of a traveling grate. That's more or less a horizontal grate. Biomass is deposited here, just outside on top, and this rotating grate, it moves very slowly. You see it here as a chain, and the biomass is transported through the furnace as it burns, and the burnt out char and the ash ends up here at the end of the grate, and it's deposited here on an ash removal system. Another type of boiler, and that's the types of boilers in the larger segment from about roughly 10 megawatts upwards, is called the fluidized bed boiler. And what is meant by fluidized bed is that the biomass actually combusts in and on a bed of inert material, which can be sand, for example, which is brought in suspension by an airflow, and the which is blown from under. And this is a small video that shows it. It starts behaving as a liquid, more or less. It is sand, but because there's air blown under it, it sort of starts to float. And by having the right velocity of the air, and the bed, as they say, is kept in suspension here. And basically, once this is achieved, the sand can be heated up, and then once biomass or other fuels, I should add, are fed into it, the heat from the bed very quickly heats the biomass that enters, and it makes sure that the different combustion steps of the biomass are followed. Of course, the combustion of the biomass heats the sand, and the flue gases coming out will then further on in the boiler be transferred to the heat. This is a interesting video of an industrial fluidized bed system. This is a so-called circulating fluidized bed boiler, meaning that the speed of the air that's blown in is a bit higher, so that the bed is actually lifted up, and it goes all the way up in the furnace, and it goes over the top, and it enters here in cyclones, where it is separated from the flue gases, and then the bad particles return back down to the bottom of the furnace, where they are re-entered into the boiler. See them here going down. And then there's some further heat exchange between the hotbed and the steam system. And the fuel was actually injected from the sides as it burns. Flue gases go here over the top. So the main heat exchange is between the bed and the water tubes in the boiler walls, and then it passes through the superheaters and economizes on the end. Now the heat transfer in steam boilers, in most of the cases, especially larger boilers, larger high pressure steam boilers, the water is contained inside tubes, and the fire of the combusting biomass, or the flue gases, are on the outside. The water tubes are typically contained in the boiler wall. Also prevents the boiler walls from melting if the temperature of combustion inside the boiler are extremely high. Inside the water tubes is pressurized water, because of the higher pressure. The water evaporates at higher temperatures, typically, let's say, a few hundred degrees centigrade. And then you have the transfer of heat from flue gases to the water tubes, either by radiation or by, well, let's say, a combination of radiation and convection. So hot flue gases passing past the colder surfaces of the boiler walls, and then the flue gases go further down the boiler, passing overheaters for increasing the steam temperature, and in the end passing through an economizer for preheating the boiler water. About the combustion temperatures, in principle, the higher the temperature, the better the heat transfer from the boiler to the boiler water. But at some point, the ash that's in the biomass can start melting. It can start sticking to well, basically to any part of the interior of the furnace and the boiler. That means that it will start forming deposits, and that will decrease the heat transfer. It increases the maintenance requirements. So it's important to keep as much as possible below the ash melting temperature. And secondly, as indicated earlier, at higher combustion temperatures, you get formation of nitrogen oxides. That's something to be avoided, because it's basically well, it's environmentally damaging, causing acid rains, and it's an emission that must be avoided, and if it cannot be avoided, it should be removed from the flue gases. Just hold on. This is a nice video of the showing the passing of the boiler water through the system. Let me see. It does have sound. I hope you can hear it. Just a moment. So actually, this reheating that's mentioned is not for all systems. It depends whether there's well, let's say a need for reheated steam in the boiler in the turbine layout. Now the flue gases, as they come out of the boiler, they might need cleaning. First of all, because there might be quite substantial amounts of fly ash contained within it, and that's the very light fraction of the ash that is carried away by the flue gases through the boiler and to the stack. And they need to be removed as much as possible because they contain the heavy metals that would be included in the biomass, which is damaging to the environment and also to humans when inhaled. Fly ash removal is usually done in different stages, and modern systems at least have, well, let's say all systems usually have a cyclone system, a multi-cyclone system that separates solids from the gas by a centrifugal force. Basically, the flue gas is brought in rotation inside a cyclone, and the solids in the gas are sort of pushed to the outside, and the gases can go out of the top of the cyclone. And multi-cyclones usually remove, let's say, roughly 80 or 90% of the fly ash. And then in modern systems, it's usually followed by an electrostatic precipitator, in which the solid particles are electrically charged by an electric field, and then they are attracted by the charge plates and thereby separated from the flue gas. that have more than 99% removal efficiencies. And there's other types of filters that can be put after that. For example, fabric filters can take out even the largest parts, the last parts of the fly ash. Secondly, as indicated, if there's large amounts of nitrogen oxides in the flue gases, then this should be removed, depending, of course, on the regulations for the amount of nitrogen oxide that can be emitted. It can cause smog, which is a problem mainly in urban areas, but also acid rains, which is a general environmental concern. And there's different techniques available for removal of nitrogen oxides, catalytic or non-catalytic. Yeah, that's. Before we take a break, I'd like to show an example that I found someone that I know from LinkedIn. I know that he's involved in the construction of a bioenergy plant, a 3.3 megawatts plant in Argentina, and they were a month ago. They were in the process of constructing the boiler, the reciprocating grade boiler, horizontal type, and there's a nice little video for that as well. So this is, you see the sloping grade, which is typical for the reciprocating grade. You see the boiler walls being erected with the steam tubes on the outside. That's the steam drum being put on the top. It's interesting to see the size of the boiler in relation to the people working on it, and the let's say the overall installation. It's a system that produces electricity and it's a limited amount of steam as well at 2 bar. We'll have a extraction condensing turbine for the production of the electricity. That's it. The turbine being installed. System will be using fresh wood chips. Well, I'm not sure when they will finalize the system. I think it should be taken into operation early next year. I'll check with my contacts on the progress that they are making. So this video is about 1 month old, so they should by now be nearing the completion. All right. I think that was it for this first part. Let me see.